Alright, welcome to Academic Digest class. Today I'll be teaching you electric flux. We normally say that electric flux, represented with this sign, is the total charge or the total, or you say the collection. So the total electric field. It is defined as the total electric field line or electric field intensity. So I will choose to use electric field intensity. I can choose yes. So total electric field intensity. I don't want to use line because the formula does not show its line. So I will use the total electric field intensity on a surface or in a given surface or in an area in a given surface. Oh God, just pray you understand, because this part of physics requires practicals a lot. Total electric field intensity on a given surface. So we normally represent it as, you see sometimes they put things like this, ignore that shit. So if I know this, I need to also understand that sometimes I can be asked to find electric fields or electric flux, but I'm not given the electric field. Yes, I might be given this and I'm not giving the electric field, or I'm told to find electric field intensity or electric field line. So if in that case, I will not apply what we call Gauss law. That's why we normally put electric flux and Gauss law together as if they are together. And you need to know that this electric field intensity, if I rush to Gauss law without telling you that whenever we are calculating this, there are some cases that require us to pay attention to the charge distribution. And this charge distribution involves you taking note of the surface. Is it a linear surface? Is it the linear distribution, or the surface distribution, or the volume distribution? So whichever one you are using will now take us to what we call paying attention to the densities. So that is why we normally say that electric flux goes to explain electric field density as well, surface density, linear density, and volume density. So it goes to tell you the density the way it is trying to tell you about electric field too. So we'll explain that more. So Gauss theorem, Gauss states that the total electric flux, he said that the total electric flux you have, or a total electric flux, is equal to, or is the sum, the total electric flux is the sum of all the charges enclosed in a medium. And we know that in a medium, which we know that the most abundant medium is vacuum. So we know that in a medium that there is something called permittivity. In a medium, once we talk about movement of electric field in a medium, permittivity. So we know that permittivity is represented with E. So, but once we talk about permittivity, there's something called permittivity of free space. We've talked about it before. So that is why you normally see this Gauss law to mean the same thing as saying total electric flux is equals to charge all over permittivity of free space. That is sum of all the charge. You can put E here for sum of all the charge, or you just say charge all over permittivity of free space. And we know that permittivity of free space, which is E naught, is equals to 8.85 times 10 raised to the power minus 12. I don't bother putting the units. It's important to put the units, but I didn't cram it. I didn't memorize it, because if you want to get this now, if you decide to make any of this, I know that electric flux is equal to volts meter. Shebi? So if I decide to make this now subject of the form, you see that this will come here and this will go here. So it's the same thing as saying this should be coulomb per volt meter. So I can put it to be coulomb per volt meter. I can put it to be F over meter. So whichever way you can calculate it. So, but that's, by the way, that's not the case here. So if I know this Gauss law now comes to play. This Gauss law that we are seeing here. So if you check it, since we know that electric flux naturally is EA, now Gauss is telling us that it is total charge enclosed in a system. That means that if I bring this and bring this together, I should be having that this is EA. That means it's equals to Q over E naught. So this is the theorem we normally make use of. The theorem we normally make use of whenever we want to find electric field, considering field distribution. And I told you that field distribution has to do with what area is it. Field distribution has to do with density. Let's put it that way. Has to do with density. Is it a linear density? Is it a surface density or a volume density? So if I know this, this knowledge that I have, this little knowledge, which you can get yours from what I've said and add to what you know, takes us to the main thing I have for us today. And that is, I will come back to this. We need to know when to solve for electric flux, when to apply Gauss theorem. We need to know that. But the main thing I have for us today is this. So we apply Gauss theorem mainly when we want to find electric field. Yes, we normally use it for calculation. You need to know it. But when to find electric flux, anytime they ask you to find electric flux, it's either you are using this, depending on what you are given, or you are using this, or you are using. But whenever it has to do with Gauss theorem, that means they are expecting you to use the combination of, which at the end of the day you might end up making E. You end up making E subject of the formula. And when you make E subject of the formula, you pay attention to the densities. If the density given, if they tell you that you are given linear density, you know that that is lambda equals to charge over charge over length. Charge over length. And if you are given area density, this is the symbol. Some books write it this way. So, but I don't want to use this one. You know that it is going to be charge over area. If how you get it is, you remember that density is equals to mass over volume. And I told you that in electric field, consider mass to mean charge. I've told you that before. See it the same way. If you like, don't see it, but just see it. I know what I have in mind when I tell you that. Now volume, for density volume or volume density, you now know that volume density is represented with P, because that is density for you. Rho, not P, is rho, is called rho. So we know that it's charge over volume. So very important as we start solving the main things. You now see. So let's now go to the main thing we have for today. This is the reason why we are here. And if you go to your textbook, the way they did all these things are very confusing. And this is the type of, or the areas that you get questions from. So case 1, I said Gauss find, that is case 1 is to find electric field. Find electric field using Gauss theorem for infinite line of charges. So for infinite line of charges, this is what we mean. This is a cup. I had to get this cup read because I can't find something that I can use to explain this better. So it's been long So if they say it's infinite line of charge, they are talking about infinite line of charge. There can be cases where they are talking about infinite cylinder of charge, so, or infinite sheet of charge. So when they are talking about this infinite line of charge, take it that this pen is the line of charge. Let's say we have the let the ink inside it to be positive, negative inside. Notice that if I put this thing here, the charges that I have on this, as is enclosed, let's say I have a covering this, and as is enclosed, the charges I have on this, we have nothing to do up here. Like up here, there will be nothing up here, no charge here. But the charge is this, as I put it here and I enclose it, it will be disturbing these walls. Everything here will be charged, like it will be going this way. So that is why when you are considering this infinite, anytime you are giving question, they tell you giving linear density, or they did not tell you. Once you hear infinite line of charge, this is the diagram you use. It's either you use it this way, that you are considering a line of charge, line of charges, and then the Gaussian surface is now like a cylinder enclosed in a cylinder, the Gaussian surface. So you need to know this. Once it's a line of charge, it can be, let's say I have it this way as well. See that enclosed in the Gaussian surface. So this is a cylinder, Gaussian surface. The cylinder is the Gaussian surface. So you need to know it is the same thing, but I drew one sleeping while the other one is standing. So if I know this, if I have this knowledge now, what this simply means is that I've now seen that up here, if you're looking at it on paper, it looks as if it's among. Up here, there's nothing happening here. The same thing with down here, nothing is happening there. So that is why you normally see that area of cylinder, which is 2 pi r square. That 2 pi r square is the same thing as saying pi r square plus pi r square is 2 pi r square. So since down here and up here is not among, I will not use this one, plus 2 pi r l. And this is the same thing as saying everything here is more like a circle. That is this sides, lateral sides of it, then and this length. So this is where the whole charge, the whole thing is happening. And the charge in here, the electric field here is moving in this direction. The electric field here is moving in this direction. So for that reason, if they ask me to find the electric field, which is in number C, option C, I'll show you how to do it. But look at this, they said find total charge enclosed by the Gaussian cylinder. So to find total charge enclosed by a Gaussian cylinder when you have an infinite line of charge, is simply for you to come back here. So for infinite line of charge, given linear density, they will tell you. So when the question gives you linear density, assuming they gave you surface density, you make this charge. So given linear density in this case, infinite line of charge, to find the charge, the total charge enclosed, it will simply be lambda is equals to Q over L. So Q will be equals to lambda L. So this is the formula you use to find the total charge enclosed. Now for electric flux through the cylinder due to infinite line of charge, which is B, I don't know the electric field. Remember that we said that we have two formulas for electric flux, EA, electric field and area, and then charge and E naught. So I've gotten this one. If I've gotten this one, that means to find electric flux here, we'll simply be using Q all over E naught, because E naught is a constant, which is 8.85 times 10 raised to the power minus 12. Then I put Q, the value I got for Q from this, and I get this. So let's move now to finding electric field at a point, say 2 meters away from the infinite line of charge. Anyhow it is, see what it means is that if I have this to be the infinite line of charge, let's say this is 2 meters away from it, or yes, this is the line of charge. So they did not say away from the cylinder. There can be questions where they tell you away from the cylinder. When they say away from this cylinder, there is no charge outside. You use you use Q in that case. But if they tell you, the question will direct you, or just know all these cases. So in this case, what I will now need to do, once they tell me to find electric field, which I told you, know when to use Gauss theorem. So we use Gauss theorem to find electric field. So we apply the combination of this and this. Gauss theorem says that electric flux is equals to total charge enclosed in a system or in a surface. So an electric flux on its own, this is the definition. Electric field and area, product of it. So it's equals to this. So applying the theorem, I will now have that this is going to be EA to find electric field. EA is equals to Q over E naught. Q over E naught. And if I have this to be Q over E naught, I will now see that first of all I need to go back and see that my charge, since I am given linear density, I keep saying given linear density or given surface density. These three things are important. So the one you are given determines what you do. So given linear density, I will simply say, remember that linear density is represented this way, all over lengths. So make charge sort of formula so that you have Q is equals to lambda length. So if I have this, I will now come and replace this for the charge up here, so that I now have lambda L all over E naught. So if I have that, it will now be equals to E A. And you need to notice we are dealing with area of a cylinder. Area of a cylinder, because this charge enclosed is happening here. So because the charges are happening inside here, that is moving this way, the electric field, that is what I mean, they always move perpendicular, yes, at 90 degrees to the normal line. So because they are happening that way, I'll say that this is going to be E times 2 pi RL. That is this one that I got here. I'm not using this one because it's not happening on the surface and on the base. So I put it, so equals to pi L all over E naught. I have L here, cancel. So to get E now, make E subject of the formula, we then have equals to lambda. Divide both sides by 2 pi R, so that I have 2 pi R E naught. That is epsilon 0. So to find, what this means is that to find electric field when you are given an infinite line of charge and you are given linear density, this is the formula you use. Note it, very important. So you can also say, if you want to still suffer yourself, or maybe you have need for it, you can also say, since lambda is Q over L, I can replace lambda here with Q over L. So divided by 2 pi R E naught or 1, so that Q over L times 1 over 2 pi R E naught. So this is also a formula I can use. If I have charge, I have length, I can put this together. So I just replace this with Q over L, then divided by. So let's go to case 2. Okay, reading the subheading, let me make drawing. So let's say we have charges. Let's say these are charges that we have. Charges everywhere. Let's say these are charges. So they say Gauss theorem. I said case 2. Gauss theorem for infinite sheet of charge that contains surface density and 2 parallel plane electric field. So we use this Gauss theorem, if you remember, when we want to find electric field. So it's the same thing as saying finding the electric field on an infinite sheet of charge that contains surface density and 2 parallel plates electric field. Now remember that surface density is given by charge over area. That is the same thing as saying, so normally we know that surface density is mass over area. So in this case it's charge that we are using. So if I put it well, then I said 2 parallel plane plates. So let's say I'm using a cylinder as the plates. You can choose to use anything you want. That is why when I'm considering this one, you will see how I'll solve it. So let's say you want to use your own as a box, no problem. Maybe you want to do, if this is like this, you now have a box this way that will protrude outside is you that know. But the problem with using box is that charge distribution will be everywhere. So if you want to do your own like this, no problem. But me, because I understand the physics I'm doing, let's say I'm using this one, something like this, that protrudes outside. So remember they say two parallel plates. So two parallel plates. So let's say this is my enclosure. Now this is the, remember our focus is on this. So but let's say I have a parallel plate running through it. So it's the same thing you have here on the textbook. So we are using this plate as our Gaussian surface. We're using this as our Gaussian surface. Remember, everything we do here always have a Gaussian surface. That's why I told you when we started that if we have a parallel that infinite line of charges, I'll come and put something like a cylinder here. This is our Gaussian surface. Why this is the charge on this one. So this is our Gaussian surface. So whenever you're thinking of it, you have that in mind. So I'll have electric field flowing this way, E flowing on this outside. Remember, I did not put something inside. It's the charge that is on this sheet of metal I had to put, so that there's an opening here and there's also another opening on this, which is E. So if I know this, there's an area on this. This is the area. There's an area on this. This is the area. And you need to note, write it down, that electric field always move in perpendicular. Like you always move at 90 degrees to the normal line of force or of charge. But a situation where it is not moving in that area, that is why we have EA. EA cos 90. Cos 90, if I have, for example, see, if I have this to be 90, by the time I look right, is 0. Cos 90 is 0, shebi? And that means this is 0. Why? When it's moving parallel, parallel means in the same direction, 0 axis. So EA cos 0. Cos 0, if I have this, cos 0 is equals to 1. So you see that if this is 1, this will be EA times 1, which is equals to EA. So this is not really where I'm going to today. So if I know this, so I'm not going to have EA. There is two things here. So I have EA on this one plus this EA, and is equals to, remember that surface density is given by Q over A. That means if I'm getting Q will be equals to surface density times A. Yes. Then remember that electric flux, the Gaussian theorem, applying Gaussian theorem, it states that EA is equals to charge over permittivity of free space, if you still remember our first class. So if that is the case, notice that the EA I have in this particular situation is 2EA. Then I have charge, replace charge with surface density, so that I have A all over permittivity of free space. So you can now see that I have 2EA is equals to surface density and A all over E naught. So I have A and I have E. Somebody might want to ask me, why don't you put this in such a way that, why didn't you put this one in such a way that you have maybe a cylinder here and another area of a cylinder here? So notice that the area I have on this is the same area I have here. So if this is a cylinder, this is also a cylinder, the same area. So that means to give way. So that I have 2E equals to surface density all over permittivity of free space. Making it subject of the formula, I have E is equals to surface density all over, divide both sides by 2, I bring 2 E naught. Don't blame me if you don't know how to make subject of the formula. So I have this, but I can say anytime I do this, I always leave my brain open, because I know that anytime you're doing mathematics, you can have different change of formula depending on what you are given. Let's go back and see that surface density this surface density is given by charge over area. So I can say, let's replace surface density with charge over area divided by 2E0. So if I do that, you now have that this is E equals to surface over A, so times 1 over 2E0. So you can see that E is the same thing as saying Q over A 2E0. Or you can say that it's the same thing as saying Q over 2E0 A. So note this. Have this in mind. So this is how to go about Gauss theorem for infinite sheet of charge that contains surface density and two parallel plates, finding the electric field. So thank you. My next class will still go on with the different cases of finding electric field. And I normally tell my students, in finding electric field, there are important keys to note. Bring your pen, write it down. Write it down now. Let me just give you an example, something I've pulled out. So the first thing is to determine the continuous charge distribution, which could be linear, surface, or volume. Divide the charge distribution into infinitesimal elements of charge and calculate the distribution of electric field at each point from each element. So express the distance and the vector as function of coordinates of charge elements. So if I know that, we'll call it a day. We'll see in our next class. So in case 3 and case 3, this is our case 3. Electric field produced by two oppositely charged sheets with surface charge density. Make that this class. So Gauss theorem, I told you, whenever we're putting this Gauss theorem in use, know that we are finding electric field in most cases, or electric field intensity. I told you electric field intensity and electric field, they are the same thing. Electric field is a region where electric field is experienced by slow moving charges. Yes. Why electric field intensity talks about the measure of or degree of movement or change in direction of charges, or you say how strong these charges experience the electric force. So but that's by the way. So if we are doing electric field of two oppositely charged sheets with surface change, then surface charge density, we know that surface charge density is equals to charge over area. So if I have this in mind, it's always important to pay attention to what you are giving. So if I'm giving surface charge density, I'll use this. Assuming they give me linear charge density, I'll use that lambda equals to Q over L. So if I have this line of charge given to me, the next thing is to make room for Gauss surface. So this Gauss surface I will use in this case because this is already this way. So I can choose to use a Gauss surface for two oppositely charged body. It's not like when I have one. So this will be attracting this one. 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 So this is moving away, moving away, moving away, moving away. So in that case, if I want to draw the Gauss surface, I can choose to have something like this. If you want to, you can choose to have your own to be a cylinder. Let's say you have something like this. It's up to you. So but whatever you are doing for this is only one of these I'm using, so I cannot use the whole charge, so just one. So I've gotten this surface now. And if I have this surface, let's say I'm considering this one, let's say you are considering this one. So what I will say is that there will be E on this, and this surface will have an area, same thing with this one. So if that be the case, it simply means that I will apply the theorem of electric flux is the total electric field on an area. So EA is equals to Gauss theorem, which states that electric force is the total charge enclosed in a system, and any system enclosed has permittivity, and in this case permittivity of free space. So if I have this, I will now remember that I can make charge subject of formula since I'm giving surface density. If you like be asking how are you getting surface density, always have it in mind what you are told. Assuming they said giving linear density, I will use that of linear, but this one is surface density given. So making use of the formula, I will have the surface density times area. So come and replace charge here so that I have EA is equals to surface density times area all over permittivity of free space. So notice this area, notice something, the area I have for this charge, which is this area A. Yes, notice this is the area of the charge because this is the one I replaced. Why the area of the surface will be the same, because notice I have this enclosed. So as I've enclosed it, the charge is in this surface. So it's not like maybe when I have, for example, if I have something like a cylinder like this now, and I come and have charges inside this, and then I have another cylinder enclosing this. So you see that I have this surface and I have this surface. I can have this one to be R and this the other one to have is R. So provided that I have this is the surface. This surface is enclosing this charge. So if the areas are the same, so I can now say cancel, so that E is equals to surface density all over E naught. So I can choose to remember the surface density if I want to complicate things for myself, or maybe the question wants to put us in trouble. I just need to remember that surface density is equals to Q over A. Replace surface density here so that E is equals to Q over A divided by E naught. So E is equals to Q over A times 1 over E naught. So E is equals to Q over E naught E. So whichever way you see it, so what this means is that this is the same thing with this. They are equal. So but it depends on what the question is, your question given to you has. So why I'm saying this is that you need to always pay attention. Notice that the surface I used, the Gaussian surface I used. This is the Gaussian surface I used. This is the spelling of Gaussian surface I used. Gaussian surface. A situation where I have, for example, a cylinder. There are questions where they can give you a cylinder. They tell you an infinite cylindrical line of charge, so enclosed with a Gaussian surface. This kind of question, if you are considering this kind of question when you are talking about the charge, you will consider charge in this area. That is the QA that you have. If its surface density will be area of this particular charge, that means it's the same area of 2 pi r L, but you use different radius because this has its own radius and this one has its own radius R. So it has its own radius, let's say small r. So that's what I'm trying to say. But notice that in this case now, if I enclose this or enclose this with a cylinder or this with a cylinder, you see that the area, these parts will be closed. There's no going out. So if I enclose this, let's say this is the Gaussian surface, you can see that the area I have here is the same thing with what I have here, and again it's just a charge enclosed. So it's not like when it is open like this other one that I have an opening, is going out and is going out this way. I know I've explained it much, but you understand if you go through it over and over, make small research. Thank you. Subscribe.